Hello, everyone. Come on in. Does anyone have any questions about anything before we get started?
Yeah, I have a question, Professor.
Go for it, Alexi.
I checked in the modules and I haven't seen the chapter 27 and 28 practice test pop up yet.
Let me check that while you're here then. It definitely was supposed to be up a long time ago. In fact, I thought I put it up before the break. Let's look here. How about this? Thanks for letting me know that you get to find it though.
Yeah,
Let's
no
see.
problem.
Sometimes I roll over a test. I did something like that. Okay, so test 4 is yep, it's just sitting there like a dummy. Okay, it is available now. Let me double check, make sure everything works with it. Sometimes when I make a test, it will actually not have questions in it, which is really remarkable. And this one does have questions in it, so we're good there. Go back to modules. All right, so your due date is on the test, which I think was Monday. It was due, or Sunday it was due. I'm going to push it back.
Says it's due on Sunday, 11:59 p.m.
Gotcha. Yeah, I'm going to change that now then. Okay, so edit. Instead of March 20th, it will now be a little faster. That would be awesome. Man, this thing's going really slow. I'm afraid the thing's going to be laggy again tonight. So I'm going to make it due Tuesday the 22nd at 11:59. And let me go up here. So I changed it to the 22nd, both in the description as well as in the due date part. All right, so now everybody notice you now have until Tuesday at 11:59 p.m. of next week to get this test done. That's on chapters 27 and 28. Tonight we're finishing up 29 and we're going to start into 30. So we're pretty much on task. After this, we're going to go to thermodynamics. And really, thermodynamics and electricity and magnetism is all we're really required to do. But here at TCC, we try to get in quantum mechanics afterwards. And if possible, even go beyond quantum mechanics and do a little cosmology. But so I'm not too worried if we don't cover those. The deal is most classes, like if you take this sequence at Virginia Tech or UVA or Chapel Hill, it's a 3-semester sequence. The first semester is mechanics and thermodynamics. The second is electricity and magnetism. And sometimes we don't do that. Sometimes we'll do electricity, magnetism, and fluid mechanics, or just electricity and magnetism. And then the third semester is all modern physics, which include relativity, quantum mechanics, nuclear physics, and maybe even some cosmology. So we try to give you a little modern physics in with our 241 covering relativity and our 242 covering quantum mechanics. So we'll see what we can do, see how that works out. Anybody else have any questions? A couple people I just let in because they obviously weren't in when I went over to my page to check the practice test. So it was announced that my practice test wasn't showing, even though I thought I'd opened it up before the break. I must have closed it back again or something. So I've now pushed the test date back. Test 4, an online test, will now be due instead of Sunday at 11:59 p.m. It's due Tuesday at 11:59 p.m. Just want to make sure. I think there was 3 people that just came in that hadn't heard that. So now, does anyone have any questions? All right, I'm going to work a problem here that's related to that voltage issue that I talked about why we step up voltage and stuff like that. So let's imagine that we have 10,000 homes. Okay, I'm going to write this stuff down as I'm saying it, so you can write down the numbers too. But then when I turn on the document cam, you'll see them written up there. So I got 10,000 homes. And each has a current of 200 amps that must be supplied. those 10,000 homes are essentially 40 miles away. Okay. And I want to consider power loss at V equals 120 and at V equals 800,000. Assuming 1.00 inch aluminum wire, then copper wire. Okay, so what I'm imagining here is, remember I told you basically a service entrance for, that's what they call it, fancy gooberish term, but that's what they call it when you talk about connecting to the power grid at a house. They call it the service entrance, and basically that's where the meter comes in, or that's where the power comes into your house, and that's where the meter's setting, and that's normally very close, if not immediately on the opposite side of the wall from the circuit panel. So each of those houses generally require 200 amps, and that's sort of the standard. That means it can supply a whole 200 amps for each of the houses. So we're getting, in this case, we're supplying 200 amps times 10,000 houses. And we're assuming it's coming straight from the power company at 120, 120 volts, not 240, but 120. There's an issue with that. But the way we do 240 is we do tri-phase electricity. So we do 120 volts, 120 volts, 120 volts, each 60 degrees apart. And when you do it that way, you have a maximum difference between a peak and a trough of 240. So we can still carry 120, but the difference is 240. So that's the way we do that. But we're just going to treat it as if it's 120 volts. And in doing so, what we're going to do is say, okay, well, let's say we have a 1-inch line. In reality, they don't have a 1-inch line. They normally have braided wire, because it's very, very hard to and expensive to have wire made that's a whole inch in diameter. So they make a bunch of smaller wires and they braid it. And that total is going to be 1 inch, but we're going to pretend it's just like solid, because there's a minor difference, but not a huge difference. Okay. What I want to do is figure out which wastes the least power, and then see if that's even remotely cheaper to do it with aluminum or to do it with copper. So that's the plan we're going after here. After this, we're going to work an example where I use Faraday's law, just like I used Ampere's law. So let me turn on the document cam. Anybody have any, before we do that, anybody have any questions about how what we're talking about on this problem? Okay, if any of you would do me a service of looking up the resistivity of aluminum and copper before we solve the problem, that'd be great too. So I will make use of that. This would be a quantity that you'd normally be given on the test, or you'd have access to your manual, to your textbook, which would have that data in a table. So what we want to know is, I'm going to say A, how much power loss is lost with 120 volts and I'll turn this thing off. I must have turned it the wrong way. With 120 volts and aluminum wire. B is how much power is lost with 800,000. Whoa, missed a zero there. 800,000 volts. And aluminum wire. And C, how much power is lost with 800,000 volts and copper wire. So obviously We're going to need the resistivity of aluminum. And we'll need the resistivity of copper. Has anybody managed to look that up yet? Oh, no.
I put it in the chat, sir.
Oh, thank you. Appreciate that. Awesome. Thanks, Cadmium. Did you see I put in your change of grade from last semester?
Yes, sir. Thank you.
You're welcome. All right, there you go. So aluminum is 2.65 times 10 to the negative 8. And that should be ohm meters, if I remember correctly. And copper is 1.68 times 10 to the negative 8th ohm meters. And what we're using here is R is equal to rho L over A. So R for aluminum would be 2.65 times 10 to the negative 8 ohm meters times, now the length is supposed to be 40 miles. So that's 40.0 miles. And I know the exact conversion. I could do that really pretty straightforward because I convert it from miles to feet, from feet to inches, from inches to centimeters, from centimeters to meters, and then I would be done. But that takes a lot of work, and I can actually just look it up in the front and they give us a conversion. That's not exact, but it's good enough. So 1 kilometer is equal to 0.6214 miles. And then we can use the fact that, oh, no, you got even better than that. 1 mile is equal to 1.609 kilometers. So I'm going to say 1 mile times 1 mile in the bottom is equal to 1.609 kilometers. So I'm going to say that's 1,609 meters, because I really want it in meters, not miles. I mean, not kilometers. So that's that. And now I'm going to do pi, because the surface area, the cross-sectional area of the wire is pi r squared. And what we said was, assuming, oh, I didn't even write it up here. Yeah, I said the words, but I never wrote it. The diameter is going to be equal to 1.00. Oh, there it is. 1.00 inches. So that's really it there. The good news is 1.00 inches is exactly 2.54 centimeters. So I can say 0.0254 meters over 2, and then square that. And of course, the calculation for copper would be exactly the same, only using a different resistivity. So I'll say 2.65 e to the negative 8 times 40 times 1,609. And then I'll say divided by, and here's where you want to use parentheses, because if you're doing any multiplying in the bottom, it's only going to divide by the first thing unless you put it in parentheses. So I'm going to say 3.14159 times, I'm putting 2.54 or the 0.0254. I'm putting that in parentheses too, because I'm going to divide it by 2. Divide that by 2, and then I'm going to square that. Whoa, no, I don't know what happened there. Divide it by 2, and now I'm going to raise it to a power of 2. And you can see on my calculator what it looks like I've done. So it's a 2.65 times 10 to the negative 8 times 40 times 1.609, or times 1,609, divided by 3.14159 times 0.0254 over 2 squared. So that gives me 3.36. I'm gonna carry one extra digit and call that 3.366 ohms. Notice the ohm meter, this has meters on top. That would be meter squared, and this is meter squared down here. So that makes it meter squared over meter squared, because so it just comes out to be ohms. 3.36 ohms. That's a lot less than I expected. Okay, so now I'm going to do the same thing with copper. So R copper, just because we're going to need it anyway, so might as well, right? This is going to be the same thing, except we're using 1.68 times 10 to the negative 8 ohm meters. So dot, 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 dot. Okay, what I'm going to do with that is I'm going to divide it by 2.65 e to the negative 8, and then multiply it by 1.68 e to the negative 8. And you'll see that I'm only getting about 2.134 ohms. So this one was 3.36, this was 2.134 ohms. Are y'all surprised at how little resistance that is? I really didn't expect it to be that small, but these are pretty realistic figures, believe it or not. So yeah, that's not that big a deal. So now what I need to do is realize the power loss for part A. Victoria's coming in. The power loss for part A is P is equal to I squared times R. I now have the R. So what I have to do is now realize what the current is. And if I step up the voltage to 800,000, what I know is V secondary is equal to the N secondary over the N primary times the V primary. So what I'm actually doing is I'm going to set this so that this is 800,000 volts is equal to N secondary over N primary times 120 volts. So that you can see N secondary over N primary has got to equal 800,000 divided by 120. And that gives me 66,666.67. Is the ratio. Okay, now we know VS is equal to NS over MP, but IS is equal to NP over NS times IP. Our IP is the 10,000 times 200 amps, and this is 1 over NS over NP. So the IP is 200 amps per house times 10,000 houses. And that'd be, that's 2 times 10 to the 1, 2, 3, 4, 5, 6, 2 million amps divided by 6,666.67 is the ratio. So I now get 200,000 or 2 million divided by, I'm just going to take that answer, and that gives me 300. So instead of sending out 2 million amps, I only have to send out 300,000 or 300 amps. So now I can take this 300 amps and say P with aluminum equals I squared R with aluminum. That's going to give me 300 amps squared times 3.366 ohms. And that's 300 squared times 3.366. And that gives me basically 302,940 watts wasted. So that is actually the P aluminum, but notice I had stepped the voltage down. So this is the voltage being at, or excuse me, I had stepped up the voltage. This is the voltage being at 800,000. So that looks like a lot, but now we can also compare it to the P aluminum for 120. That's still going to be I squared R, but in this case, we're going to have to do the whole I squared, which is 2 times 10 to the 6 amps squared times 3.366 ohms. Remembering I'm using 1 extra sig fig. That was 1, 2, 3 is the right number. So all of these are doubtful digits. This is a doubtful digit. So when I do this, I don't know why I labeled this A, because I'm sort of doing everything at the same time. So I'll say 2e to the 6 squared times 3.366 gives me 1.346. Make sure I'm seeing this right. Yes, 1.346 times 10 to the 13th watts wasted. So you can see for part A, now let's go ahead and write the answers, even though I sort of labeled that part A. Let's erase that and just call this solution. So for part A, it said how much power is lost with 120 volts and the aluminum wire. That is 1.35 times 10 to the 13th watts. Part B, how much at the 800,000 volts? That's 3.03 times 10 to the 5th watts. So literally that's a factor of 8. 10 to the 8th is a factor of basically 100 million times worse in the A case than the B case. And now in part C, they want to know how much would be wasted at that if I use the aluminum, the copper wire instead of the aluminum. So now I'm going to do P aluminum, or excuse me, P copper. Copper is more efficient of a conductor. So I'm going to say P copper, and this is going to be 800,000. So the only difference here is I have that same 300 amps, but instead of having 3.36, I'm going to have 2.134 ohms. So 300 squared times 2.134. That gives me 192,000. So I'm going to say 1.92 times 10 to the 5th watts. So the percent decrease to go from, let's say going from copper to aluminum, that's supposed to be the difference divided by the initial. So we're talking 3.03 minus 1.92. Notice the 10 to the 5th all cancel out, divided by the 1.92. And you go 3.03 minus 1.92. Whoa. Evidently, I didn't hit the minus. I hit it, but it didn't take. So now I divide that by 1.92. That gives me about 102% basically. Or excuse me, 1.02. So that's a 102% decrease in the cost, which is good. I mean, you can see it clearly went a lot cheaper, but comparing it to doing the 800,000 volts versus the 300, or excuse me, versus the 120 volts, that was a way bigger change. Any questions on that? So this little percent thing, that was just something extra just to tell. If you, it seems, you know, worthwhile, but when you look at the cost of copper versus aluminum, I think you'll discover that copper is way more expensive than aluminum. I don't remember what the weight or the cost per pound of aluminum was, but I did used to, you know, do little side jobs where I go and cut down those large satellite dishes that people used to have that were like, you know, 6 foot in diameter or something. I'd go with my truck and pull them out of the ground, and then I'd cut them up with just a circular saw. It's pretty amazing that you can cut them up with a circular saw. Well, they're made out of aluminum. I had to cut them up because if they didn't fit into the this, I think they call it smelter, if they don't fit into that, then they give me less per pound. But you know, one of those whole things would only cost, I mean, would it only fetch me about 120 bucks. If that was made out of copper, I suspect it'd be like $400 or $500. So that might be twice as cheap using copper than using aluminum, but in terms of power loss, but it's probably going to be 3 or 4 times as expensive to use copper instead of aluminum. So that's why they do mostly aluminum and not copper. Any questions on that? Anybody need to see any part over again?
Yeah, I had a question on the percent decrease.
Yes.
I tried double checking, but I didn't get 300. I'm sorry, I didn't get 102%.
Okay, let me check my math too. 3.03 divided, oh. Yeah, you're right. There's something happened there. I can see my calculator. I don't know what it did, but it didn't do what it's supposed to do. 3.03. Thanks for catching me on that. Minus 1.92. That gave me 1.12. Now I'm going to divide that by 1.92. Yeah, I thought that was a little high. So thanks for checking. Yeah, that's 58.3%.
Did you do 3.03 minus 1.92 or 3? I got 57.8%. I wasn't.
I did 3.03 minus 1.92 and then divided it by 1.92. And that gave me, go ahead.
I got 57.8%.
Oh, yeah, I see why. So the first time, I don't know what the heck I did, but check this out. So that was me subtracting 3.03 minus 1.92 on the money. Then I went to divide by 1.92 and evidently I hit 1 and then accidentally hit multiply with my fat finger. That's why that came out, the 1.02. And the second time I did 1.91 instead of 1.92. So yes, you're right. I'm wrong again. Minus 1.92. So 3.03 minus 1.92. Thanks for checking me on that. Now I divide that by 1.92. And that gives me a 57.8125%. Thank you.
You're welcome.
So it's actually more like a 57.8% decrease in waste. Now, this actually does contribute, for instance, to by a small amount, of course, to global warming, because that's basically what's happening is the wire's heating up. That's heating up the environment, so on and so forth. But again, it's from a financial standpoint and actually from a global warming standpoint, the sum of all those wires is very small compared to just, you know, methane from cows alone, much less methane from cows and humans and everything else. And then the carbon dioxide, of course. But yeah, that makes more sense, because I expected if this is really going to be a double, then this should have been more than 4, and it wasn't. So nice follow up on that. Appreciate it. All right, now I want to do a problem sort of like the well, actually, it's going to be more or less the same problem as at the end of chapter 29. What we're going to have is a strong magnetic field between 2 poles, a north pole and a south pole of a magnet. and that magnetic field is going to be uniform between those two circular poles, really uniform, exactly within the range of the two circular poles. And what we're going to try to do is calculate the generated EMF if the current, or if the magnetic field that's coming from those poles changes as a function of time. So this is not unlike example 2914. So what we're going to do is we're going to imagine we have, this will be example 2. We're going to imagine we have, looking from the side, let's say I will do a north pole of the battery of a magnet here, and this is actually going to be quite a bit smaller than I'm showing by scale here. We'd actually have the distances really small compared to the diameter, but I just wanted you to be able to see it. And of course, we've learned that magnetic fields are like old people. They come out of the north and go into the south. I know that's a little disrespectful, or could be taken disrespectfully. I don't mean it that way, but it's just a good mnemonic to teach you the direction that the north, that the magnetic field points. So it's going to point down basically. And what we're going to say is that the magnetic field actually changes by an amount dB over dt is the change in B. So these little lines in here are B. Okay, now once you get out here, it essentially goes to 0 compared to everything else. But what we know is Faraday's law is in action, and Faraday's law says the closed integral of E dot dl. Notice that's just like Ampere's law, except it's an E instead of a B. The closed integral in magnitude, at least, will be equal to d phi b over dt. Now remember, it's normally a negative and there could be an n in there. But we're just working about magnitudes right now. So normally and times n. But again, that's for like a number of poles is what the n is for. Now, if you had to use Faraday's law in an equation, then yeah, you want to go ahead and stick the negative in there. But if you're just trying to calculate something like this, you don't need to do all that. Now I'm going to look at this from above. So magnet as seen from above. So I'll say CI, which means okay. So imagine looking down on it from above, like that eyeball drawn there. Okay. Now, when I do that, what I basically am going to see is the magnet, which is a circle, like this. And since I'm looking from above, the magnetic field lines are going to go into the page. So there'll be an X there, 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 sort of, an X there, sort of. In other words, it's really going to go off to 0 right there rather quickly. And so on and so forth. So that's a fairly uniform magnetic field. Now, what I'm going to do is first consider this is a radius big R. And I'm going to consider an Amperian loop whose radius is first smaller than big R. Okay. And its radius is little r. But in this case, since we're doing Faraday's law, it could be a Faradayan loop. Okay. Now, what we know is the flux is changing dB dt. We don't know if that's really a positive change or a negative change. If we assume that the magnetic field is increasing, assume dB dt. Actually, let's assume it's decreasing. Then dB dt would actually, I'm actually assuming that B is decreasing. The dB dt would be less than 0, and that would make this not have a negative sign, which would eliminate the negative sign. Okay, so now by doing that, I'm not cheating. I'm not just getting the magnitude. I can actually deal with it. So we're saying the magnetic field points down and the magnetic field is decreasing in time. So Lenz's law tells us that it's going to oppose the change in flux. So is that going to try to strengthen the magnetic field in the loop, or is that going to try to weaken the magnetic field?
Strengthen.
Yes, it's going to try to strengthen it. So Lenz's law suggests a B induced would be into the page to strengthen. Well, strengthen the decreasing B field. So it's going to create a magnetic field that points into the page and says, so what kind of current causes that magnet or that magnetic field to be induced? So I induced is in the blank direction. Anybody tell me the answer to that?
Clockwise.
Yes. In order for you to have a magnetic field into the page, you have to take your fingers like you're grabbing a wire. Remember, you grab a wire with your right hand, you put your thumb in the direction of current, your fingers curl around the wire in the direction of the magnetic field. So my thumb is pointing into the camera. And that means if I wanted if I had a current going into the camera, then the magnetic field would be counterclockwise. In this case, I want an actual magnetic field to go into the page in the middle. So if I grab that wire like that, my thumb is pointing here at the bottom to the left. So that is in fact a clockwise current electric field. So I is clockwise. That's I induced. Now, remember, I is only induced by a voltage, and that's what E dot dl is. So that means the electric field is actually going to be parallel to this to make a current go that way. That's what wires do, is they sort of corral the electric field so that the current runs along the electric field's lines, if you will. So now we have that, we can say hypothesis. First off, I'm going to do this and say this is my positive x-axis and this is my positive y-axis. And the reason why I'm doing that is you can see now that points in the theta hat direction. So my hypothesis is that E is equal to E of some R times the theta hat. In other words, it acts in the theta hat direction. Again, theta hat doesn't necessarily mean anything. It's from the polar coordinate system or the cylindrical coordinate system. I'm just using it to indicate that it's going to be perpendicular to a radial line at each point. So here it'll point there, here it'd point that way. So you can see it's always tangential to a circle. That's why we make that hypothesis. Then DL is going to equal R d theta, theta hat. So the left-hand side, closed integral E dot dl equals the integral E of R theta hat dot R d theta, theta hat. The E of R and R are constant because E of R we expect only depends on R, and R is a constant, and then R of course is already a constant. So we just got theta hat dot theta hat gives me 1. So I get E of R times the integral of d theta from 0 to 2 pi, and that gives me 2 pi R E of R. See how that went, just like Ampere's law? The right-hand side is because dB dt is assumed to be negative, it becomes positive d phi b over dt. Okay, but phi b is b times pi r squared, because we're counting the part that's enclosed within the loop that we chosen. So it's only out to a radius r, and that r is less than big R, which I'll notate right here just to make sure we remind ourselves that. So what this becomes is pi r squared times, times dB dt. So left-hand side equals right-hand side gives me 2 pi r E of R is equal to pi r squared dB dt. One of these r's is going to cancel out. This pi is going to cancel out as well. So I get E is equal to, basically you can see it's proportional to R, and it should be dB dt times R over 2. All of that in the theta hat direction for R less than big R. So that's part of the answer. Now I want to calculate the electric field out here. So I'm going to take an Amperian loop for this part. This case, R is greater than big R, as obviously shown there. So for R greater than big R, left-hand side, I should probably stop writing in red. The left-hand side is going to become closed integral E of R, or I should just say E dot dl. Okay, my hypothesis was that again, E should be E of R theta hat. So this becomes integral E of R theta hat dot R d theta theta hat, which becomes again 2 pi R E of R. The right-hand side, however, is d phi b over dt. Well, phi b is still going to be, in this case, the entire flux is just this part here. Because remember, the magnetic field is going to get, it'll still exist outside the R greater than big R, but it's going to be so small compared to what it is in here that it's essentially zero. So what I'm going to get is I'm going to get B times pi R squared plus 0 times pi R minus big R squared. And it's going to be the derivative of all that, of course. Because what I had to calculate was the derivative of the flux. Well, the flux is going to be B times pi R squared because it's uniform all the way out to big R. But then it's going to be approximately 0 for R bigger than big R. So all the rest of the part is going to give you 0. So I'm just going to get pi R squared dB dt. So left-hand side equals right-hand side. In this case, gives me 2 pi R E of R is equal to pi R squared dB. Actually, no, that vector somewhere. Sorry about that. dB dt. So ultimately, what we can see is E, the vector field, is equal to 1/2. That's what how I'm interpreting this over here. I'm going to take it as 1/2 dB dt R theta hat for R less than big R. And in this case, the pi's still cancel out, but I'm going to get 2 R squared dB. No, I'm going to get 1/2 R squared dB dt over R theta hat for R greater than big R. And if you notice, if you substitute big R in here, that actually gives you the exact same expression you had for big R being in there. So they actually are continuous. So I can put an equal symbol in there as well. So I'm going to write this as R squared over 2R dB dt. That should look a little better. So in principle, what that looks like, E as a function of R should be linear up until it gets to R, and then it falls off like 1 over R squared, or excuse me, like 1 over R. And you could even mark this point as 1/2 R dB dt. Any questions on that? That finishes chapter 29. Okay, no questions? Everybody gets that? But now you're starting to see one of the cool things about this is this looks like the electric field is acting just like the magnetic field. We found this to be the case for basically a current carrying wire going straight up. The current going straight up had a magnetic field that was proportional to R for R less than the radius of the wire, and for R greater than the radius of the wire, we had it go like 1 over R. And it was radially around it, just like this is. So the electric field, you can see in this case, is very much just like the magnetic field in that it even goes in a circle, but it goes in a circle around magnetic field lines when they're changing, whereas the magnetic field goes in circles around current, which is changing positions of charges, I guess is one way to look at it. So I'm going to kill that. And we now have these 2 pages. So that brings me to chapter 30 now. Chapter 30 is called Conductance electromagnetic oscillations, and AC circuits. So we're going to obviously cover that stuff. This is a pretty in-depth chapter, so there's a lot of things we can do. So I'm going to say it's definitely going to take today and at least next class time, but it might even take a third class time. And this is 4th edition. Okay, so what we're talking about initially is something called mutual inductance. So if we had done the, let me turn off this and put on my camera, my webcam. So if we had done the Faraday's lab experiment, which we used to do, and we haven't been able to do it this time because we do it early in the semester, and early in the semester we were under quarantine sort of thing, so we couldn't actually meet face to face. But one of the things we discover is that if you take and, for instance, run a current through a wire, and you take that wire and spool it up into like a solenoid. We've seen solenoids before in magnetic fields that come from them. But if you did that, it creates a really strong magnetic field inside of the solenoid. Well, if you happen to just connect another solenoid to, say, a galvanometer, no battery, just a galvanometer, and bring that solenoid near the first one, or the first one near it, you will get a current flowing, but as soon as you stop moving, it's going to disappear. And you can flip the experiment and do it with the second solenoid, put the power source on that one and put the galvanometer on the first one, and the same thing happens again. So there's something where one loop of wire gets compelled to do what the other loop of wire is doing, just because the other loop of wire has a current going through it and creates a magnetic field. Well, the ability of one thing to do it to another thing is something we call mutual inductance. So this is what allows you to lay your Apple Watch, say, on the back of a little disc of metal, because in there is basically, you can imagine a coil of wire sending current around it. That's creating a magnetic field that's either going down through the metal, through the little plastic disc that has metal in it, and out somewhat, because remember, magnetic field lines don't stop. So if it went out the bottom of the disc, it's going to come back around and come in the top of the disc. And by doing that, that's going in through the top of the watch. And the watch has something sort of like that, in that it has a loop of wire. So that magnetic field will now generate a current inside of that wire inside the watch and charge the watch. The same thing happens, for instance, when you have a cell phone that lays on its back on top of its charger instead of plugging it in. So that relationship between two coils of wire is called mutual inductance. And then we can also talk later, and this is the more important thing. We're not going to do very much with mutual inductance. We're going to do something called self-inductance, or just plain inductance. And that self-inductance is basically, hey, what happens when I jam a current through a solenoid? Because we know Lenz's law is going to kick in. Like if you start ramping up the current going through a solenoid, Lenz's law is going to say, hey, I didn't have any magnetic flux going through the solenoid before, and now I do. So it's going to fight to oppose that change in flux. So it's going to create a magnetic field pointing in the opposite direction, and therefore create a back current, or a back voltage, or something like that. Okay. That's just plain inductance. So let us get started by just talking about what mutual inductance is. So we've defined mutual inductance. Say the mutual inductance of 2 due to 1. So the mutual inductance of 2 due to 1. And let me see if I want to make sure I'm using the same notation that the book is. So I want it, before I write 2 due to 1 or 1 due to 2, I want to make sure I'm using consistent with what the author says. So we'll let phi 2,1 be the magnetic flux in each loop of coil 2 created by the current in coil 1. Okay, so yeah, it is 2 due to 1. Okay, so that mutual inductance of coil 2 due to coil 1. Okay, so what we're going to do is we imagine this is coil. Mutual inductance M21 XA. If coil 2 contains N2 closely wrapped loops, then N2 phi21 is a total flux passing through coil 2. If two coils are fixed in space, N2 phi21 is proportional to the current in the coil. The proportionality constant is N21. It looks like they said specifically 2 due to 1, but then the diagram, it looks like they drew exactly the opposite. So
Professor, Dr. Younger, could you please refocus the camera?
Oh, yeah, that went bad. Thank you.
No problem.
Okay, appreciate that. Okay, so this is coil 1. Okay, I see. Yeah, I see what they did. So this is coil 1 right here. And what they have is a current I going through it. Okay, and that would be, say, current I1. And then next to this, and it doesn't have to be next to this, there's all sorts of ways you can orient it, but next to it turns out to be sort of the best way. So now I have coil 2 right next to it. And that has nothing connected to it, but because this one's got a current going through it, it's actually creating a magnetic field, let's say this way. And you know, it sort of goes a little quicker than that, but I'm trying to show that the field lines do extend into here, but not necessarily as far as I'm showing here. Okay, well, what we found is that the the mutual inductance on 2 due to 1 is actually equal to the number of turns that coil 2 has times the magnetic flux of 2 due to 1, and then you divide that by the current I1. We know that E2, according to Faraday's law, is negative N2 times d phi21 over dt. Of course, if you try to take the derivative of that, you can use the expression above and you get E2 is equal to negative M21 di1 over dt. In other words, if you solve this for phi21, you get phi21 is equal to M21, which is a constant based on the geometry and stuff like that. M21 times I1 over N2. Whoa, N2, I don't know why I wrote that. So once I solved that that expression for phi21, if I take the derivative of this, obviously the M21 and the N2 are constants. The I probably isn't. So the only thing that survives is this N2 cancels out with that N2, and all I get is M21 times di1 over dt. That's important because that, when we go to use Kirchhoff's voltage rule, you know, his loop rule where you add up all the changes. Well, the change in voltage across an inductor will be inductance times di dt. In this case, it happens to be mutual inductance. In the case of circuits, it's normally L, which would be the self-inductance, which is also just called inductance. Okay. So that's what we define this to be. It's just the mutual inductance. And, you know, if you're an engineer, that's one of the electrical engineers, and you're working for, say, Apple or something, that's one of the things they got to make sure this M21 can be large enough so that you can actually not just waste a buttload of electricity by sending out all this magnetic field line from the platform that you lay your phone on. Meaning that if they're so far apart, then obviously the little ring's not going to get much flux, and with that small amount of flux, it's going to take forever for your phone to charge or your Apple Watch to charge. So that's what mutual inductance is. If you wanted to, for instance, calculate the mutual inductance of a situation like this, you could say, okay, let's imagine a really nicely wound solenoid. So you got a super smooth solenoid. Like this. Okay. And then you got this crappy loop of wire running around it like that. Okay. This one has N2 lines, N2 loops, and this one has N1 loops. The cross-sectional area is A, and we are actually sending a nice current this way, and that's called current 1. And this length right here, say, well, actually, I better make it a cursive L because L is what we're going to use for the inductance symbol. So this is all just a really nicely met one. And you might want to calculate, say, the mutual inductance of M. Let's say you might want to calculate the M21, M12. So if you wanted to calculate the mutual inductance of 1 due to 2, that would be hard because you wouldn't be able to calculate the magnetic field for this loosely wrapped solenoid, right? Just to remind you, these are actually sort of not seen because they're behind the solenoid. Okay, so that's bad. But it turns out that experimentally and essentially theoretically as well, M21 is supposed to be the same thing as M12. So if I wanted this, that would be a nightmare to calculate because I don't know what the magnetic field due to this crazy shape is. However, if I use the fact that M12 is equal to M21, I do know when you have a really nicely wound solenoid exactly what the magnetic field due to it is. So I can say M21, which is the mutual inductance on 2 due to 1, then all I have to do is realize that that's going to be the number of coils N2 times the flux 2,1 over the current I1. Okay. I also know that the magnetic field in N1 is equal to mu 0 N1 over L times I1. So the magnetic flux would be B times A, which is just mu 0 N1 over L I1 times A. So now if I want to know what the mutual inductance is, I just say M21, which is the same as M12. Therefore, we're just going to call it M. That's going to be equal to, I just plug all this in, I get N2, or let's do it this way. I'll first put in the mu 0 from that, and then I'll do N1. And now I have to have an N2 in there as well. So I'll put the N2. And now I'm back to the I1 times A. And then I'm going to divide all that by I1 and L, because the L was already in there from being under the N1, right? So you can see that ultimately what happens is the two currents cancel out, and I get M is just equal to mu 0 N1 N2 A over L. Okay, so this is actually a result that you're allowed to use. Your book didn't number it, but I will allow you to use it. So if you answer any questions with mutual inductance, it's almost certainly going to use this answer. You don't have to go through and derive it. Okay, I just want you to use it. So I'll say this is allowed on equation sheet. Okay, even though it's not numbered, it's allowed on your equation sheet. Any questions on that? See how good this works now. Yeah, I'm getting a little better there. Still can fit the same page. Okay, So that's mutual inductance, and that's much more complicated. And again, I'm not going to do much with that. You can see what we just call chucker problems, where they're plug and chug is another word for it, where basically you're just going to take the formula, assume it applies. Obviously, you should put some thought into whether it really applies or not. And if it doesn't, then, you know, be prepared to answer, I don't think it applies here. And therefore, maybe it's one of the choices would be cannot answer this, or not enough information, or something like that. Other than that, I wouldn't expect you to do any more mutual inductance calculations. Now, the other part of this chapter is what I do expect you to be able to do. And I've been hinting at that since literally like day one. And I think you saw one of them on your midterm. So what we did before, once we got into Gauss's law, we used Gauss's law to get us the electric field. Then we used the closed integral of E, or excuse me, the integral of E dot dl to get the voltage. And then we use C equals Q over V to get the capacitance. Okay. Now what I'm going to do is I'm going to want you to use Ampere's law. And in actuality, we didn't have to use Gauss's law. That's just normally the way we do it, so that you can use Gauss's law. We could have used Coulomb's law and then went from there, and that works fine. Similarly, we could use the Biot-Savart law, and that would work fine. But we're going to use Ampere's law usually to find the magnetic field. Then we're going to use the definition of flux, which is, this was delta V equals that. So this is the flux sub B is equal to the integral of B dot dA to calculate phi B equals question mark. And then we're finally going to use inductance is equal to, so this is the new equation that you're going to learn. It's equal to N times phi B over I. You can see how that's a natural extension of what the mutual inductance was. The mutual inductance had N over I times the flux, the mutual flux from one to the other. This is just the flux through the thing. And from that, you're going to calculate L equals question mark. So that's the two similar problems that you have to be able to do. So for instance, let's look at the solenoid, the inductance of a solenoid. So this is a new quantity. Mutual inductance and inductance both have the fact that the mutual inductance and the self-inductance, which is also just called the inductance, has units of, if you look at it, it's Webers, 1 Weber per amp, right? But that turns out to be such a valuable quantity that we use it over and over, and it's called the Henry. Okay, so that's the unit for the mutual inductance, that's the unit for the self-inductance, that's the unit for the inductance, which is the same thing as the self-inductance. Now we know the expression for it, and this is the new big equation that you just learned. Well, two of them. You learned the mutual inductance equation, like that, and that would be 2,1. But you also learned M21 is equal to M12. So that came in handy. And then that gave us that expression, but these are your new things here. So what I'm going to do is imagine a solenoid and calculate its self-inductance. And let's say the solenoid, so example 4, maybe. I'm counting that last one that we just did with the mutual inductance. I counted that as an example. So this example 4, we're going to imagine a solenoid now. Ideally, it's the same number of circles on the top and the bottom, but I'm not counting or trying to keep that perfect. But by putting the dots up here in the middle at the top, that means the current's coming out of those, and these X's down here means the current's going into those. So the current comes out, loops like this, and then goes back in that way. So you can sort of imagine it doing this to each of those wires. So this comes in here, and this would be the one that comes out like that, say. And this would be the last one. And this would be the one that comes out, say. Okay, let's say this solenoid has N turns and a length. I want to use lowercase l for the length. Not that we necessarily need it. We have the I there. And what I'd like to calculate is I want to do this process. I want to calculate the magnetic field, then calculate the magnetic flux, then calculate the self-inductance. So first off, I'm going to apply Ampere's law. Ampere's law says the closed integral of B dot dl is equal to mu 0 times I enclosed. Okay. So what I'm going to do is imagine a little Amperian loop. I think I'll do it on this side right now. And my little Amperian loop is going to go right along the middle here and come back out here. And you have to have it consistent with the current. So in this case, I'm going to say along here, B hypothesis, so I'll put a little H on that, is going to be equal to B of R times, let's say, I hat, because I'm assuming my coordinate system is like that, and that would be Y, say, okay? And R would just be basically the distance from, it would basically be Y. In this, by symmetry, you can use it as Y, so I'll call that Y instead of R just to make it more consistent with the diagram. So that's my hypothesis. That's why I subscripted it H. And it's going to be that everywhere in here. And out here, I'm going to assume that B hypothesis is approximately 0. Okay. So the left-hand side, yeah, I'll write it with red. Left-hand side, closed integral B dot dl is equal to integral, and I'm going to say B of Y I hat dotted with, now along this particular line, the DL is going to be DX I hat. Along this particular line, the line is going to have to go down this way. So it's going to be plus B of Y I hat dotted D negative DY J hat. Now along this one, notice that's half and half part B of Y and the other part B equals 0. In other words, when you're inside of here, it's going to be B of Y, but once you get out here, it's going to quickly go to something closer to 0. So I'm putting B of Y in there, but I realize I'm only going to integrate, say, along here to about this point, and then from there on, it's just going to be 0, which is going to give me 0. Over here, I'm down at this part, and that's going to be integral of 0 dot negative dx I hat. Okay. And then I got to do this part here too. And I'm going to say plus again, B of Y slash 0 dotted with, in this case, it's positive dy j hat. So that's really what's going on. We've got to do a closed loop. That's why that circle's on there. So I'm not just doing this part. I'm doing the whole thing, but the deal is when I do this part, I get B of Y times L, where L is this little itty bit right here. let's call this, let's say L1. Okay. When I do this part, notice the dot product gives me 0 because it's I hat dot J hat. And even when that's not the case, when it gets out here, it's going to give you 0 because the magnetic field's 0. And then when I get over here, the magnetic field's essentially 0. So I'm going to get 0 for that. And then for the same reason as I did over here, I get 0 for all this part. So ultimately, all I have is B, which doesn't depend on Y at all, as we can, as we'll see in a second. But B of Y times L1 is what the left-hand side is. The right-hand side, on the other hand, the right-hand side is mu 0 times I enclosed. Well, as long as the right-hand rule applies, then this is a positive current. So if I use my right-hand rule and think about which direction I'm going around here, right? Then if I'm going in a direction that's consistent with I going into the page, then I'm okay. So if you look here, I going into the page produces a line going that way, a line going that way, a line going that way. So this is consistent with that magnetic field pointing that way, which is the only part we care about. So I'm just going to call this mu 0 times N over L times L1. Okay, if I take the total number of curls or total number of turns per whole length L and multiply that by the actual length, then I get the number of turns in that little bit, and then that's times I. So now I can say left-hand side equals right-hand side. And this one's going to give me, you now see no Y dependence, so I'm just going to write B times L1 is equal to mu 0. There's a symbol for this. It's called the lowercase n. So it's lowercase n times I times L1. You see the L1s cancel out, and ultimately I have B is equal to mu 0 n times I, all in the I hat direction, and basically is 0 outside. Now, obviously, if you get really close to this end, you're going to have a significant magnetic field, but if you go far enough away, just a little bit further, it's going to disappear rather quickly. So that's why I'm saying the B outside is 0. So now I have the magnetic field, which was step 1, Ampere's law. Step 2, I've got to calculate the flux. Well, the flux in this case, we're trying to calculate basically what flux would generate a current. Well, the flux that would generate a current would be the flux of the magnetic field through the cross-sectional area. So if we turn this so that we're looking at the solenoid like that, then we can look right here and say this is our area A in the solenoid. Okay, so the magnetic flux is equal to the integral of B dot dA. But luckily, this B is constant all the way through, essentially, right? It's strongest, to be honest with you, right along the center, but generally we make the radius of this fairly small, so it's essentially the same everywhere. So we're going to say this is just B times A, which actually equals mu 0 n I times A. So now we've got step 2. Now, step 3 is we want to use L is equal to N times phi B over I. Well, that means L is equal to N times mu 0 NIA over I. So we get the self-inductance for a solenoid is going to be equal to, now we can actually substitute the N over L here, and I'm going to say it's equal to mu 0 n squared times the cross-sectional area divided by L. Notice the i's cancel out. That's a hallmark of this equation. Just like I told you, capacitance should never depend on the actual charge or the voltage or anything like that. It should always be just in terms of the geometry. The same thing is true about inductance. It should only be related to the geometry and that sort of thing. So this is actually it. That's the expression. And this is the process that is sort of the capstone for, I would say, the last 5 chapters that we've done, 4 or 5 chapters that we've done. The first 4 or 5 chapters, the capstone is using Gauss's law, delta V equals negative integral of E dot dl. I forgot the negative there. Sorry about that. E dot dl and C equals QV. That's the capstone assignment for the first part of chapters 21 through say 25. And then 25 or 26 through 29 is this. Okay, there's other things too, but these are sort of the bare minimum that I would like everybody to get. So this is something you need to be able to do over and over and over. Come final exam, you need to be able to do both of these, the Gauss's law process and then the Ampere's law process. And of course, we still need to know how to integrate Coulomb's law and that good thing, that good stuff. Any questions on that? You can also do this, for instance, for a coaxial cable. So let's look at one of those types of problems. And again, I'm doing this. Your book is not doing this way. I'm doing it to keep you current. I'm actually starting from the bare minimum with Ampere's law instead of just using the result that we already know from Ampere's law. Okay, that's because that's what the way I'm going to word the problems. I will make it as if it's one problem, but really it's like a 3-step problem that you got to do. So I'm rehashing what we learned in Ampere's law instead of just taking the results like they said. So let's imagine the inductance per unit length. So this is example 5. Find the inductance per unit length of a coaxial cable let's see, with inner radius A and outer radius B. Okay. So what we're going to imagine is we have a coaxial cable, radius A, that's the inner one. We have an outer one whose inner radius is B. And this, in fact, goes back like that. So that's the coaxial wire. You'll notice this does look like the cable wire that you get from DirecTV, Dish Network, or cable television. The difference is they normally have just a solid little bit of copper wire coming out the center, and it's very thin compared to the radius of the whole thing. This all in here is some fluff, basically. It's a dielectric, but there's paper in there. There's some kind of plasticky material. And then out here, this is just braided wire, aluminum wire is this outer part. And that's another conductor. So that's exactly what this stuff is. So first off, I want to calculate with Ampere's law to determine B. So I want B inside of in between the two plates. So what I'm going to imagine, just so my coordinates work out really nicely on a coordinate system and that sort of thing, I'm going to imagine that this right here is my positive x-axis, and it's actually lying on the front of this. Now, lying on the front face as well is the y-axis, and then into the page, of course, or into along the center of that cable is the axis z, and that gives us a right-handed coordinate system. Okay, so I'm really looking like this, and then this. That's the coordinate system I'm using. My hand's all in the way. So there's x, the black one pointing out like that. There's y like that, and then z is pointing back this way. So what I'm going to do is I'm going to use Ampere's law, which says the closed integral of B dot dl is equal to mu 0 I enclosed. And I'm going to say hypothesis. So we're using our physical intuition to guess that since this is an infinitely long coaxial wire, that the magnetic field should only have a component that's parallel to the XY plane. It's not going to have any Z component whatsoever. So my hypothesis is that B is going to be some B of R, the cylindrical coordinate R, times, let's say, theta hat. And I'm saying theta hat because I'm assuming the current in this wire goes this way. Okay. Then the left-hand side becomes closed integral B dot dl is equal to the integral of B of R theta hat dotted with R d theta theta hat. Remember, just in case you aren't picturing it already, the Amperian loop we're using is a concentric circle right here. And of course, I'm going around it in a clockwise fashion as seen this way, which is exactly the sense that it should be going, given that the current's going in there. So the mu 0 I is definitely going to be positive. Of course, since we're doing it along that constant radius R, and R is between A and B, by the way. So since I'm doing that constant radius R, this R and this B of R both have to be constant. So I end up getting just 2 pi R times B of R, whatever that might be. The right-hand side, on the other hand, is mu 0 I enclosed. And notice the current is going in. So if I grab that current with my thumb pointing in the direction of the current, which is right down the shaft of that center bar, then my fingers are curling around in the same direction that I did my integral. So that's a positive current. So I'd get, this is mu 0 times I. So now I can say left-hand side equals right-hand side. Oh, crap, we're way past time. I'm sorry, guys. I'll finish this up. I'm way past your time. I just realized it's 6:14 and class is supposed to be over at 6:04. Everybody's free to go. I'm going to finish this up, but you don't have to stay. It'll be on the video. I did have problems with yesterday with Monday's video. That's going up tonight, and then I'm going to put this one up immediately after. I'm sorry I kept you so late, guys. Feel free to tell me. I won't consider it rude. So thanks, guys. Sorry about that. All right, for those of you who still stuck around, or for whoever can watch this video later, I went way over time not paying attention. That's a total newbie mistake. So I'm going to set the left-hand side equal to the right-hand side. I'm going to get 2 pi R B of R is equal to mu 0 times I. You can see there's no, well, there actually is an R dependence in here. So I can now say that B is equal to B of R times theta hat. Well, that's just mu 0 I over 2 pi. That pi turned out terrible. 2 pi R in the theta hat direction And that's just for R between A and B. So I've now got step one. Step two is I want to calculate the flux. Well, the flux in this case, what's relevant is like a rectangular area that you might say is radial, but it goes from the outside edge of the inner cylinder to the inside edge of the outer cylinder. So its length right here is B minus A, and we might take the length right here to be L. So part two is flux phi B is equal to the integral B dot dA. Well, that's just going to be, notice the B depends on the radius. So that's a little bit more complicated. The dA is going to be perpendicular to that. So that's going to be in the theta hat direction as well. So I'm going to get the integral mu 0 I over 2 pi r theta hat dotted with dA. What I'm going to imagine is my little dA element is this. Okay. And that thickness is dr, and this length is L. So I'm going to say L dr, and of course that's also going to point in the theta hat direction. So I can now say that I get mu 0 I over 2 pi, and then L is going to be up here as well. Integral of theta hat dot theta hat is 1, so I just get the dr over r. And I'm going to integrate it from r equals A to r equals B. So I ultimately get phi B is equal to mu 0 I L over 2 pi times the natural log of B over A. So that's another useful result. And now we're left with the last part, 3. Again, man, I really went over time limit here. Now I want to use L is equal to N times phi over I. This is only one turn, so the N's irrelevant. So the induction is going to be mu 0 I L natural log B over A over 2 pi divided by I. So you can see the I's cancel out, and I get L. Remember, I asked for the inductance per unit length, so I'm going to divide by L on both sides. That'll get rid of this one and pull it over here. So that's just going to become mu 0 times the ln of B over A over 2 pi. And that's it. That's the inductance per unit length. You can plug in some numbers to calculate if you want, but that's it. Sorry again for running over class time. Let me scale scan over this so everybody can see it one last time in the video. But this process is something you should be able to do. You should be able to do it with a cylinder like I did here, or a solenoid like I did on the previous example, or with a toroid. So those are your normal 3 scenarios. And of course we can soup it up with other ways, but if you look at the answer or the problems in the end of the chapter, you'll see a lot of different things you can do. So that's it. Have a good day. Alexi, do you have any questions? Thanks for checking around.
Actually, yeah.
Go
Can
for
you
it.
scroll down to the part? Yeah, right there is fine. I just need to get the intermediate step from the integral in part 2 to the flux of the magnetic field.
Right.
Also, when you took the integral for A to B of the flux of the magnetic field, how did you get from dr over r to, like, where did the r go?
Oh, the integral of dr over r is natural ln.
Okay.
Or the natural log, the ln, sorry. So yeah, that's where it went. And it's just weird because the A and the B, instead of me using RA and RB, it doesn't look like it has anything to do with radius, but it does. A's a radius and B's a radius.
Yeah, I was just confused because I was thinking, like, it was r squared. But
right.
it's a negative exponent, so then
Yeah, the way I remember it is, differentiating, you subtract one. With integrating, you add one. Anytime you're adding or subtracting one that you get 0, that means you're running to the log thing. So that's the way I
Yeah.
keep track of it. So if I had to add one to negative r to the negative one, that tells me, oh yeah, that's the log.
All right, I got it. Thank you,
No problem.
Professor Dr. Younger. See
No
you
problem. Have a good one, bud.
next Monday.
Yep. See you then. Don't forget to get your test done by Tuesday.
Okay, thank you.
See ya.
Bye-bye.